Hello, everybody. So last time we were able to develop a set of equations making use of the partition function that give us the probability of finding a particle in a given state. Today, I want to go ahead and spend a little bit more time talking about kind of the consequences and the mechanics of how this works. So one of the ways we can make use of the Boltzmann equation is by looking at a simple two-state system. So all I'm going to be trying to do is determine the likelihood of finding a system in an excited state. So we're going to go ahead and kind of work this for a set of simple systems. So we're going to be looking at a case where my excited state has an energy of about 50 inverse centimeters. So if you're not familiar with it, inverse centimeters is a unit of energy that is very commonly used in spectroscopy. So 50 inverse centimeters is essentially right at the bottom end of an IR spectra. So let's go ahead and figure out how likely I am to find that excited IR vibration if I've got a temperature about room temp or 300 degrees Kelvin. So I can go ahead and do this by making use of my Boltzmann equation, where the probability of finding it in this in my state I is going to be related to the exponential of the energy of the state that I'm looking at over kT times the sum of all possible cases. So in this case, it should be fairly simple, as this bottom term, which is really just my partition function, is only going to include two possible states. Either an energy of 0 for the ground state, which we are going to always arbitrarily assign an energy of 0, and the excited state of 50 inverse centimeters. So this state shows up both as the state of interest, my excited state, 1, but also in the denominator as part of the partition function. So another useful thing to know is we can also express the Boltzmann constant in terms of inverse centimeters when you're talking about spectroscopic phenomena. The Boltzmann constant has a value of about 0.65 inverse centimeters per Kelvin. And we multiply this by the temperature, do the same thing for both the denominator, or for the numerator, and as part of the denominator in that second term. And we have a value of about 0.787 over 1 plus 0.787. So this means that I've got a probability of 0.44 of finding my system in the excited state. So roughly about 44% of our particles are going to be in the excited state, or about 56% of the particles will be in the ground state. Now, one of the cool things about this is you can start to see how this might change with temperature. So what should happen is as I increase the temperature, this value should go to about 50%. As the second term starts coming closer to 1, and then I essentially am going to asymptotically approach an even distribution of ground state versus excited state. But we can also examine what happens if I decrease the temperature, which in this case, since I already had such a high probability, really emphasizes the point almost better. So again, I'm going to return to my Boltzmann equation. My partition function behaves almost identically, still have an excited energy of 50 centimeters. Only thing that happens is now the temperature difference, I now have a different temperature value, which shows up here. And again, remembering that beta is the same as 1 over kT. So these two expressions are identical. So using this, we can then crunch the numbers, and we've watched my numerator essentially drastically drop down from about 0.8 to 0.91. So it goes way down. And doing this, it drops my probability down to about 0.08. So this means I'm down to about 8% of my particles are going to be in this excited state. And this really helps sell that as the system becomes cooled, the ground state also becomes increasingly occupied. One way of thinking about it is that my particles no longer have enough energy to regularly jump up. And this is going to become more and more true as the temperature goes down. But what's going to happen if I say change the energy of the excited state? So let's say I go from 50 inverse centimeter to 500 inverse centimeters. These are your classic, carbon-carbon bends, which give you all that noise at the bottom of an infrared spectrum. So what's the likelihood of I'm going to occupy an excited carbon-carbon band? Well, again, I can go back to my good old friend Boltzmann, plug in my value of 500 inverse centimeters, along with my original temperature of 300, plug it in, and something very interesting happens. Because now my probability, my numerator is still 0.091. And again, similarly, that 0.091 also shows up as part of the partition function in the denominator. This gives me, again, that 0.08 probability, or 8%. And you may notice that this is the exact same probability I got for decreasing the temperature down to 30. And this should make a lot of sense because essentially it's going to be equivalent whether I increase the temperature or the energy levels by a factor of 10 or decrease the temperature by a factor of 10. What both of these changes do is they both equally affect the ability of particles in this ground state to jump up. Either I make the particles less able to jump, I essentially hobble them by going down temp, or I essentially raise the bar so they have just as hard of a time. And it is cool to notice that at least when you're talking about a two-state system, these two contributions are going to be equal. Though it is worth noting that these trends do become a little bit more complicated when you go to 3 or 4 states. But it really helps illustrate that another way to decrease the occupation of excited states is, again, by increasing that energy jump. So one of the useful things to do is also think about what this does, what these changes in energy levels and temperature do to the partition function. So we can kind of, again, demonstrate this for a two-state system. As I increase the temperature, I'm going to watch this partition function go up from a value of 1, where only one state is in control, to as the temperature goes up, I'm now increasingly occupying that those other excited states play an increasing role. So my partition function is going to increase as more and more states add a significant contribution. However, it is worth noting that at a certain point, we start to see a linear sort of increase. And eventually, what we're going to find is we kind of reach this kind of plateau, because no matter how much I increase the temperature, I'm still going to always favor that ground state a little bit more. And we can also see this by looking at what fraction of the population is in the excited state versus ground state. Again, low temperatures, again, with respect to the energy gap, everybody's in the ground state. As the temperature goes up, it slowly starts decreasing, and we see an equivalent occupation of that first excited state. And this continues essentially till you get to more or less where we started, where you have temperatures that are about 10-fold greater than our energy gap, where at this point, we're roughly now equal occupation of the two states. So again, this ratio of temperature to energy level really is going to dictate where we're going to tend to find our particles. And again, it is worth noting that it's easiest to demonstrate this with, say, a two-state system. You can also demonstrate this with systems where there's multiple energy levels. So again, what we're going to tend to find is at low temperatures, my partition function tends to be fairly close to 1, as only the ground state really plays a significant role, and I may have a little bit of contribution from a first excited state. But as my temperature starts going up and up and up, we're going to find more occupation of these excited states. And this is going to be, this essentially comes through two features. First of all, each of these excited states has a greater probability due to an increased exponential function, but also as each one of these states has a higher probability, what we also tend to see is that the partition function itself gets larger and larger, which essentially decreases the probability of finding the system in the ground state. And you'll notice that you can even see this with maybe the first excited state, where there's this kind of crucial middle ground where it becomes highly occupied. And then as you increase the temperature further, its probability also goes down because that partition function essentially plays a much larger role in driving the population of these high states at high temp. Now, what we often care the most about is what this means in terms of chemical behavior. And we can drive two big take home implications about topics we've already talked about. First of all, when I'm talking about reaction equilibrium, if I'm just looking at energy levels, I'd always tend to expect species to occupy the lower energy state. So endothermic reactions should never occur because I'd have to go from a low energy to a high energy. However, one of the things that drives the occupation of products of an endothermic reaction at high temperatures is I start to occupy more of these high energy states on my reactants. So it's going to be easier for these states to drop over. And if I have more densely packed states on my product, it's going to be easy to occupy those densely packed states. Similarly, this is going to be the almost exclusive driver of why temperature increases reaction rate. So if I have, say, an energy barrier at about this energy level, so sitting at about here, as I increase the temperature, I'm really not going to be able to get any states that are able to surpass that that activation energy. But you reach this crucial point where you've added enough or your temperature is high enough that you're regularly having states occupy energy levels higher than that transition state. So they can proceed past that transition state, driving the reaction forward. So this is what really, at a molecular level, drives high temperatures, pushing all reactions forward because everybody starts occupying high energy states. So every reaction will go faster. So this helps kind of summarize our basic take homes for looking at probabilities and partition functions. Next time, we're going to try and focus a little bit more on what this means in terms of the partition functions of individual molecules. Until then, take care.